Hello, this is the project with me and Taylor, Josh and Taylor. Today is Monday, April 2nd, and we will be explaining translation, transcription, and everything around that. Now, I don't know if you can see, since this is a camera, about this, but here we have adenine, guanine, thymine, and cytosine. Now these are our four bases right here. And basically what we start with is, let's start with a nucleotide. A nucleotide is created by a base, phosphate, and sugar. Okay, we have a base, phosphate, and sugar. Okay, now they will connect. They will more or less bond with the sugar and the phosphate, connecting one nucleotide to the next. So we'd have right here a thymine nucleotide. Now, what happens here is once we have each nucleotide, they tend to bond with other nucleotides, say an A nucleotide and a T nucleotide, bond by what is called a hydrogen bond. Okay, so they'll bond to each other. After they are getting their DNA, getting their RNA, they'll find one just like it and bond. And now a hydrogen bond is one of the weakest types of bonds, and there's a reason for that we'll show you later. And now there is only, each base is only has one thing it can base with, as is a thiamine right here can only pair with an adenine, and a cytosine can only pair with a guanine. For instance, a G can pair with a C, and an A can pair with a T. Okay. Now there's a little bit, there's one more base that comes in later, but that's during translation and transcription, okay? And that would be uracil, okay? That is represented by a U. Now it still has a phosphate and a sugar. However, during transcription and translation, there is no thiamine nucleotides floating around waiting to be translated or transcripted. There is only uracil, and this acts kind of like a substitute for T, the T nucleotides. For instance, say you have a adenine, you have an adenine right here. Instead of it, if this is in transcription and translation, a thiamine won't come in to pair with it, because the thiamine isn't there. There are no thiamines, so a uracil comes in and pairs anyways. Okay, now let's come over to the DNA translation. Now, I don't know if you can see it, but here we have, along here, a DNA molecule. Okay, one rotation of the helix, which is 10 rows. Okay, we have a CG, an AT, a CG, an AT, a CG, an AT, a CG, an AT, a CG, and an AT. Now, this is one rotation of a helix, a double helix. And what happens is, and these can arrange anyways. You can do a TA first or an AT. It doesn't matter. Okay? So now what happens is a little guy right here called RNA polymerase. He comes in, and what legitimately he does is breaks the hydrogen bonds in between each of these. He breaks them. Think of like a coat. You're just unzipping the coat. Unzip each little notch is a base, is a nucleotide. You're just unzipping it. So he unzips this. He's coming through here, breaking the hydrogen bonds, unzipping it. Okay? Now, for transcription and translation, they can only use one strand, okay? One strand. The other will just kind of float around, reconnect later, okay? So, here, what's going to happen is we're going to use, say, this strand right here, okay? Now, what's going to happen here is it's going along, and there are little things on here called promoters, okay? They're going to basically, like, make a big flashing sign, like, hey, come here, come on, let's bond, you know, stuff like that. So this is going to attract them. Or not so much attract, but basically shows them that there's stuff here, okay? Called promoters. And so, nucleotides, random nucleotides are going to come in. Let's start with a U, okay? Now this U nucleotide, this is uracil, okay? He's going to look for an A. So he just comes in. So, oh, he found one. Okay, there we go. Now remember, there are no thiamine, so U has to go with A this time. Here comes a G. G goes, he finds a C right off the bat. Now, they go through, and if there is none, they just go out again. But they keep on going through and pairing up. Here's another G. He comes in, takes him a while, doesn't fit, till he finds another C. Okay? Here's a C, comes in with a G, and so forth. An A, a G with a C, a U, this is another uracil, that would go with an A. An A with a T, a C with a G, and an A with a T, okay? Now, what's going to happen here is these guys, we have translated it, okay? This is the original part, and these are just nucleotides that have come in and are bonding now. They have essentially bonded this way with their phosphates and this way with their hydrogen bonds. Now what's going to happen is they're going to break apart again, but not the original DNA piece. This is going to stay here. But what's going to happen is this one RNA strand that's been broken apart is going to head over to the ribosomes, okay? The ribosomes are in the cytoplasm, okay? Oh, excuse me. One important part, okay? They're gonna reach the stop codon when they're together, okay? And the excuse me, sorry, wrong again, okay? That comes in later. Now what happens here is these go to the cytosomes, the cytoplasm. Today's just not a good day. These go to the cytoplasm in their order they are now, okay? They go to the ribosomes. And the ribosomes basically make the information into the protein, which is what we're going to show you, okay? They go in here, and based on... And now there's something here called the promoters and the cytosine. Now the cytosine is going to come and read this. So they break it off. Each 3 nucleotides are what we call codons, okay? Each 3, like a GCC, that would be a certain molecule, a certain protein, a certain atom, or what, like, say, for instance, we would find out of this maybe melanine or something, some chemical on. So what would happen is these would all, once they're lined up, the cytosine, which I have somewhere, he would come in and he'd read this. He'd say, oh, these 3, they're certain molecule. These 3, certain molecule. These 3, a certain molecule. Now, based on that, based on which order it's arranged, what is where, it could be infinite. There is infinite number of possibilities what it could arrange as. But what happens is here is the stop codon. He's down here making wherever he is, there's a certain number. There's a, like, say for instance, AGA. You get that? That's a stop. That could be a stop codon, but you get a certain sequence of numbers, and what that will do is that will make the set design stop. Say stop. That is enough reading. Here is when you're supposed to stop, and it could happen anywhere. What makes it is it could change the. It could say the set design starts here. Okay, he's reading up, but he doesn't get to the end. He stops here. The protein is going to be smaller. It doesn't read all of this over here. It just reads this. It's going to be smaller, a different function. Again, endless possibilities. Now, what we're going to do here is, once these are all still in the ribosomes here, they're just going to kind of fold up, okay, into their certain functions. Say, like, whatever molecules they have, folding up, translating into their proteins. And now I think that is all. Thank you for watching. 11 and a half minutes long. It's not bad. This is Josh and Taylor, our project. Okay, thanks.